What up, Doug?
Not much. Mitch, how's your day going?
Well, I'm just here, just enjoying the nice, lovely weather here in sunny Seattle.
Tell you what, it's an awesome day here in the wonderful world of Kentucky. Yes.
Well, I'm a little jealous. Summer's here. Summer's arrived. Ugh. So, Doug, what are we here to talk about today? I think you got a question for me.
So, what exactly is copper bird testing?
What is copper bird
I
testing?
hear that, and it's like I've never met a copper bird. I've met all kinds
Well,
of birds, but not a copper one. So,
well, hell, Doug, you know what? I think I might have a little information for you.
oh my goodness, thank you. I was up
Yeah.
all night last night thinking about this.
Well, you can't go hunting for copper birds if you don't know where to find them.
Uh,
So, copper bird traditionally in a traditional aircraft is take a whole airplane and then take away everything in the airplane except the electrical system. So we're talking the APUs, we're talking the backup generators, the power conversion, all the lines that go to your little computer monitor, the outlet for the coffee maker, and you put it in the room. Maybe a couple 100 square foot room. You got the right lengths of the cables, and you run through electrical sequences to understand why quirky things happen in the aircraft.
Hmm.
So Copper Bird is you basically run a flight sequence of an aircraft with just the electrical network, and you're looking for power quality. Is that electricity um, at a level we would call stable? So, can we trust this, or is this going to have flicker where the lights dim, or even worse, if the avionics dim?
Ooh,
That would be bad. So it's used for that. That's kind of the traditional copper bird, and it's also used for fault testing. So let's say you're up in the airplane, and you hit play on. I assume you're watching Die Hard. At the same time, the coffee maker's turning on, and at the same time, something's going wrong in the back, um, and it dims the lights. Well, the airline's going to send that information back to the airframer, and they're going to run through that flight sequence to figure out why things went wrong.
Hmm.
So these are quite long tests where they're really looking at what's happening in the aircraft. Now that's traditional aircraft, Doug, and I think we're here to talk about a little eVTOL. So what if I one upped you? What if I one upped you with the next era of Copper Bird?
Man, this
Are
is
you
not.
ready for that?
I hold on. Let me strap myself in here. Okay.
All right.
All right.
Now, for those of you not familiar with eVTOL testing, it's electric vertical takeoff landing. We have another video where we kind of go through what is an eVTOL at a high level, so it might be worth watching. But yeah, the Copper Bird testing for an eVTOL, we've got the same traditional electrical network test where we have a room with all the cabling, but there's a new one that we're looking at called the Propulsion. Um, and these electric vertical takeoff, they now have distributed propulsion with multiple electric motors and inverters pushing a lot of power into a lot of different areas. And to be honest with you, the whole power quality environment is going to be changing. We need to understand the electrical characteristics of these propulsion networks
Hmm.
for both fault testing. What happens if I lose a motor? For control, how do I control if I lose a motor? And in these really stressful situations, can I trust the power quality on this aircraft? So it's the same, but a little cooler because now we have things spinning.
So is all this testing and everything done in a lab, or do you actually do it in an aircraft? Or
I think that's a really good question, Doug. And we're seeing a little bit of an evolution. So I think that let's talk about the problem a little bit.
okay,
But you're right. You're asking the right question. Is do we do this in a lab? So in these eVTOLs, safety is critical. And if you watched our previous video, we got 4 to 10 different powertrain configurations with anywhere from 4 to 24 motors, I think we've seen. So there's a lot of different electrical configurations, which is fun.
mm-hmm.
The eVTOL certification is currently evolving.
Yeah,
I mean, the standards need to change.
they have to. Yep.
just to fit these new unique problems. I mean, these are really novel systems. And I think the biggest one is there are a whole lot of default conditions we never had to consider before. In a system with 6 motors, how do we handle the loss of 1 or 2? And
Yeah,
which ones are we losing? Is it a
exactly.
symmetric loss? Or is it one side or
Yeah.
the other?
And all of a sudden you start turning a circle that you don't
Yeah.
want.
Well, no, I mean, you're trying to get from point A to point B. You can't just be doing sky donuts.
Exactly. Yep.
Transition states, some of these motors rotate. We're going from vertical lift to forward flight. That's pretty traumatic transition on any sort of power system.
Oh yeah.
So how do we handle this in different weather conditions?
Yeah, because from my understanding, from an electrical standpoint, the transition from very hot to very cold can really degrade the life of the electrical system.
Oh yeah.
And
Or
typically, okay, if all your electronics are inside, all right,
yeah.
you can maybe control that a lot better. But now
Mhm.
you've got electric motors that are on the outside of the aircraft.
Oh yeah. Yeah. And you got wind gusts, you got rain conditions. I mean, there's plenty of research for normal helicopters on hovering in the rain.
Yep.
Uh, you've got, I hit a bird while I'm getting a southeast gust and I'm transitioning. How do we test all these different repeatably, reliably? And this to your original question, Doug, is do we test these in vehicle or do we test these in the lab? Because in vehicle, some of this we can repeat, but that southeast gust while you're hitting a bird and losing a motor while it's raining,
Yeah.
that's going to be pretty unrepeatable.
Pretty much.
you know, um, from the fault conditions side, fault conditions are difficult and dangerous, and actually really hard to repeat in flight testing, like we just mentioned. Looking at a loss of rotor test with a pilot, or even if it's autonomous, the vehicle is an expensive asset.
Oh yeah.
That's risky, and wind conditions are hard to replicate. Bird strikes are difficult to replicate. Loss of motor can be dangerous, and these multiple motor loss configurations, again, dangerous to drivers, dangerous to people on the ground, dangerous to assets. um now we have seen some people, so that's the in-flight. We're doing in-flight testing for this,
Okay.
as much as we can, especially getting initial data. Nobody's hating on that, but it's just not very repeatable, especially
Right.
for some of these harder fault conditions. So some people are saying let's make like a iron bird rig where we got the physical propeller or multiple propellers. Well, these are cool. These are good. These iron birds are great, but they do have prop wash.
Right.
So unless you're operating in a wind tunnel, your results are not exactly good because you're getting that back force. So you're not really able to predict what's happening that well.
Right.
Um, and still, bird strike's difficult. Multiple rotor loss is difficult. Wind conditions are still difficult. And to really do it correctly, you need a wind tunnel. And Doug, I don't know if you've ever rented space in a wind tunnel.
I not lately, and I not even sure where the closest wind tunnel is to myself.
I Yeah, I don't either. But they're not cheap. They're highly utilized, and it's challenging. I mean, a wind tunnel is a great place to do this. But even some wind tunnels, you have trouble with the transition because then you need a multi-axis wind tunnel, and that's its own interesting animal.
Oh yeah. Yep.
So, Doug, you asked the perfect question to lead into my next point: is how can we repeatably, reliably, safely test some of these things?
I hope you're going to tell me because I can't
I
wait. Oh,
am
okay.
very excited about this. Um, so we're calling this the propulsion copper bird. If somebody's got a better name for it, please reach out. But we've done this a handful of times now. We're seeing some really interesting projects. So let me lay it out for you. Let me lay it out for you.
All right.
We got an aircraft that, let's say here has 6 motors. We got 1, 2, 3, 4, 5, 6 in these little groupings. Well, we want to test these motors and their motor controller. So why don't we take, your motor controller and hook it up to a vehicle simulator. We got a computer that's simulating the flight sequence and simulating the faults, the wind, the rain, the different conditions. So we got a simulation of the flight profile, and we've got either a simulation of the controller or the actual flight controller talking to that. Cool. We got one condition met. Well, we've got this flight profile and controller now talking to our actual aircraft motors and motor controllers. And that aircraft controller is saying, hey, I'm experiencing these flight conditions. Do this, do that. So we're giving it the actual vehicle commands that these motors would be receiving from the actual vehicle controller. Going to the real inverter, the real motor. And now, Doug, you might say that's fine and dandy. We did that in the in-vehicle. We did that in the Iron Bird. What's the difference? Well, in this multi-rotor propulsion test stand, we have all 6 motors. And these motors are now connected to what we would call a dynamometer or a simulated propeller.
Right.
So we've got a fake propeller that can respond as fast as we want. And this flight controller, this simulation of the flight sequence is telling these simulated propellers, all right, act like there's a eastward gust. Act like there's a bird strike on propeller 2. Act like we're in a transition wind state.
That seems like a lot of data coming in. I mean, for 6 motors. I mean, what are the different parameters that a manufacturer would measure during a test?
Yeah. So while we're running these flight sequences, and Doug, that's a great question, is what are we measuring? And I think it comes down to, what does the engineer care about? But let's say you care about everything. Because if you're running one of these tests, you probably do. Well, we're looking at the DC network. We're measuring voltage and current for the battery that the battery's outputting, because we want to understand, is that stable? When we talk about power quality from the traditional copper bird, that plays right in here. Is my DC bus stable? Because I'm pulling a ton of power from 6 motors.
Oh, yeah.
So we're probably measuring voltage and current on the 6 different DC buses. We very well could be measuring 3 or 6 electrical phases of electricity coming out of the inverter. If we want to understand, how does my inverter handle a bird strike, or how does it handle rain on half the vehicle, we probably want to look at, what is my motor controller or my inverter doing? So, now we got 3, 6, 9, 18 phases of electrical, because we want to understand how each of these controllers interact, or we want to understand their efficiency. And then we very well could be measuring torque and speed, and likely are, because you need to measure torque and speed to really understand, what is my propeller doing? So that's the propeller feedback and understanding what are those propeller dynamics. So you're potentially measuring a lot of data, and we could be looking at a small segment of the flight, or we could be looking at a whole flight sequence. So this test could be, 2 minutes, or this test could be 20 minutes, or even longer if we have a longer battery pack. But it's a great question, because we can also start to measure vibration. We can start to measure, acoustic noise in the motor. We can start to make a lot of measurements.
Well, okay, hypothetically speaking, where would I find a system like that will, have all the transducers, be able to acquire that amount of data? And from what I understand, that data could be high frequency. It could be low frequency. How do you combine them?
You ask a great question, Doug. And, I think before we hop into that, setting up this test is these dynamometers can accurately simulate these propeller dynamics. So before we go to test the data, we can look at, all the different conditions this vehicle sees. We can simulate these different fault conditions, because like you mentioned, this is high frequency data. So maybe we want to take a small segment of that flight sequence and trigger high frequency data. These things are safe and repeatable. So when we're testing, we can do them over and over again and see how my different engineering decisions affected those data results. we can start to use these data for certification. And the big advantage is we avoid that prop wash or wind tunnels. So before we go to take the data, we've really set up a very, very repeatable, predictable test scenario with these different, dynamometers and motors. So now we jump into measurement. We got the test set up. Now we jump to what HBK does. And I think this is really cool. So the HBK solution is we offer real-time computers through a brand called Concurrent Real-Time, CCRT, that can act like that flight simulator, that can simulate that controller if need be. We have an eDrive power analyzer, which let me tell you,
no, I'm excited.
And data recorder, where we can measure at a megahertz rate, up to 2 megahertz. We can record the data for really as many channels as you have and as much hard disk space as you have. So if you want to run a 20 megahertz, or a 20-minute flight sequence with 24 channels of data at 2 megahertz, you can really easily record that. It's a lot of data.
Well, but if you're going to the time and effort to set up this test, because to me it looks like that could take quite a bit of time. To get this test laid out, all the different test conditions. Why would you not want to record the data? Because to me, I don't see how you could analyze all that data properly on the fly.
And you're spot on. And when you're going for certification and you want to show I did all these different fault sequences, you want to have all that data as a backup, because you don't necessarily want to rerun these tests. The cool thing about the eDrive is that it'll measure the voltages and currents at the high frequency, but it'll also measure temperatures at a lower frequency to understand, how much is my motor heating up during these fault conditions. We can run triggering. If you really only care about a certain fault sequence, you can trigger and just catch that fault sequence to reduce that data.
Wow.
We can measure accelerometers. We can measure torque sensors. We can measure speed. So you can start to get that, if this happens in my DC bus, that happens in my torque. If this happens in my flight sequence, if I hit a bird, this happens in my current and my torque. Really understand that if then. And in addition, from that vehicle controller, we can take out, all of the CAN bus commands or the high level commands and understand, what is my controller's fault output? If the controller has a fault, what is that telling my motor?
Well, and again, that I would assume that all that data is time aligned, because you're potentially looking at a sequence of events. This happened, but when it happened, how did this react type thing?
And you have that digital data, you have that electrical data, you have that mechanical data. It's a really powerful system. You could have, 6 distributed systems time aligned, or you could have one central system taking all that data in. But we can record that data at a really high rate for a very long period of time.
Nice. Very nice. And I would think you would also, from sort of a maybe audit standpoint, you would want that data.
Absolutely. When the regulators come knocking, you want to have that backed up. And, people might say, if you're taking 28 channels at a megahertz, that's a lot of data. If you compare that to a traditional copper bird test on let's say 787, there's a few hundred channels on that test running at comparable data rates. This is nothing. It's a drop in the bucket for data for what our eDrive system can do. So to your point, Doug, you can take a lot of data and have that for the regulator, or have that for your own engineers to understand what's happening.
Well, and I would think also from a safety standpoint, you would want the highest accuracy you could get.
Absolutely.
If you come in and say, okay, well, this value is this plus or minus 20%, it's like, okay, well, no, that doesn't cut it.
No, and accuracy is always at a premium. And we have some really nice software features for looking at the harmonic content, that traditional power quality measurement. for looking at faults and triggering and identifying faults. And to be honest with you, Doug, we don't make this full test stand. We're not making dynamometers,
Right.
but we have a lot of partner companies who are. We've worked on these types of tests before. They're not cheap. They're not easy, but they're repeatable. They're really high quality. And in the long run, if you're going to be successful, they're going to save you quite a bit of money and headache. And when you go to that regulator, you're going to have something that's really, you could put your stamp on.
Well, and I would think, from a cost standpoint, that the dynamometer, okay, yeah, it's a huge investment, but it's not like you're building a new dynamometer every test.
No. You get you one, and then you run all your tests.
Yep.
So yeah, it's an exciting new test setup we're seeing, and we really think that to go to the regulators for your power quality, for your fall conditions, for your different standards you need to apply to, this is the way. And we've seen this be hot enough recently where I hope everybody's looking into it.
Can you use this system to do any type of like tuning? From, say, an inverter standpoint or anything like that? Because I think that's one of the advantages, isn't it, of electrical, is you can do some tuning. Or am I way off base there?
Oh, you are spot on, Doug. We look at it. We're seeing it with electric vehicles today, cars. Is the inverter's born, the motor's born, and it goes out into the field. Well, the engineers have a clever idea one night. They tweak a couple things and they increase the range 5%. That's something where these things are software upgradable, and we'll see how the certifying bodies handle that. That's a different thing for aerospace. But even in the development phase, rather than looking at faults, you could say, all right, we want to tune X, Y, and Z for the sound quality. We want to tune X, Y, and Z for the range of the vehicle. We want to tune X, Y, and Z because we're scared of this one event happening. And you can really start to tune your inverters, like you said, Doug, to respond to these different things differently, or increase the range, or reduce the heat, or reduce the noise. So yeah, this could absolutely be used through a flight sequence to understand if my vehicle's performing better. Yeah, it's a great point.
Well, and I would think also, just because of the inherent nature of an electrical motor, it's sort of like a step input, right?
Oh yeah.
So now all of a sudden you're bolting many of these propulsors onto wings of aircraft that have structural modes, and one of the things that is bad for structural modes is a step input.
Oh yeah. Well, and that's part of the reason I think we start to measure, accelerometers and look at the torque, because you put that step input in, and then you can see it in the torque, or you can see it in the vibration. And, as you and I have found, those structure guys are starting to be real worried about those motors.
Oh, yeah. Yeah. Well, now, I mean, you went from having 2 or 4 on an aircraft to 12.
Yeah.
So.
Oh, yeah. Yeah. I don't know. It's going to be interesting, but, we're really excited for the clever tests people are coming up with. And a system like this allows you to take all of the data and distribute it across groups and take it to the regulators and really have confidence in what you're doing, rather than just testing in vehicle with unpredictable conditions with questionable data quality. I mean, this is really high data quality, really repeatable. And so you can start having those intelligent conversations with different organizations in your company, with different regulators, to get your vehicle in the sky. So I hope people found this interesting, Doug. I hope you found this interesting.
I did. I mean, okay, I come from the structural world.
Yeah.
You come from the electrical world. And most times those two worlds never meet.
We got no interaction outside of, I need a hole for my cable.
Exactly. Well, now all of a sudden with these new vehicles, these two worlds have collided.
Oh,
That's simple.
We're right next to each other. Yeah.
So,
yeah. It's exciting stuff.
Thanks, man. I really appreciate you enlightening me on that. So.
Well, Doug, I look forward to your session when we talk about ground vibration testing.
Ooh, you're gonna love the flutter, because I know you do. Woohoo! All right, man. Thanks.
Take it easy, Doug.
See you.